We are now familiar with the large signal model of the MOS transistor. In this lesson, we will look at the small signal model. Okay. Now, the large signal model is given here. The small signal model, of course, depends on the operating point, and in each region we will have a different expression for the small signal parameters. Okay. Now, the region of most interest to us is this, the saturation region. In cutoff, of course, there is nothing, the current is 0. So, there is nothing in the small signal model. The small signal current, the incremental current is also 0. Okay. Now, in this case, in the triode region, there will be some incremental model, and in the saturation region, there will be another incremental model. Okay. So, we will consider these now. First, we will look at the small signal incremental model in the saturation region. Okay. This is the complete expression for the drain current, and of course, we know what the small signal model consists of. In general, it consists of these 4 elements: Y22, Y11, Y12 V2, where this is V2, and Y21 V1, where this is V1. And we know that in a MOS transistor, Y11 and Y12 are 0 because the gate current is 0. So, this resistance is an open circuit, and this current source is 0, also an open circuit. And Y21 is the partial derivative of I2 with respect to V1, or ID, the drain current, with respect to VGS, the gate source voltage. And that we can easily get by differentiating this, and it is equal to mu1 Cox W by L times VGS minus VT. Okay. And when we refer to a MOS transistor, we do not use the generic terminology Y21, we refer to this as GM. In general, GM is the symbol for trans conductance. Okay, that is the transfer conductance from port 1 to port 2, and this Y21 will be referred to as GM in the context of the MOS transistor, and its expression is given here. You can clearly see that it depends on the operating point. Okay. Now, for the values we had taken, where mu1 Cox W by L is 100 microampere per volt square, and the threshold voltage VT is 1 volt, you can very easily see that for VGS equals 2 volts, GM will be 100 micro Siemens. Okay. This term in parenthesis here, VGS minus VT will be 1 volt. This constant is 100 microampere per volt square. So, the transconductance is 100 microampere per volt or 100 micro Siemens. Okay. And Y22, which is the partial derivative of ID with respect to VDS or V2, okay, is of course 0, because you can see no dependence on VDS in this expression. Okay. We will later see that this is only approximate, this will not be exactly 0, but we will consider that aspect later. Okay. And again, in the context of the MOSFET, we do not use generic terminology like Y22, this is called GDS, the drain to source conductance. Okay. So, now we can see in saturation region, the model of the MOS transistor is very simple. These two are anyway 0, and Y22 or GDS is also 0. Okay. So, this is also an open circuit. So, the MOS transistor simply consists of a voltage controlled current source whose value is given by this. Okay. So, the small signal incremental model of the MOS transistor in saturation region we will have the incremental voltage V1, which of course we refer to as VGS, keeping in consistency with the terminology of the MOSFET. The voltage V2 will be VDS, and this current is GM times VGS, and the conductance is 0. Okay. There would be a conductance here, but because the drain current has no dependence on the drain source voltage, this conductance is 0. Okay. And the expression for GM is given by mu n Cox W by L times VGS minus VT. So, if you have a certain load resistance and if you want to obtain a certain gain, you know how to calculate the value of GM, and then from that you can figure out what operating point the transistor must be set. Okay. We will come to the amplifier example later. Now, let us look at the small signal incremental model in the triode region or the linear region. Okay. The expression for the current is mu n Cox W by L VGS minus VT times VDS minus VDS square by 2. Okay. Now, again we will have the same model with y11 and y12 being 0. We will have y21 V1, which in the terminology of MOSFET is GM times VGS, and y22, which in MOSFET terminology is GDS, and this voltage is VDS. This transconductance GM is given by the partial derivative of ID with respect to VGS, which you can easily work out to be mu n Cox W by L times VDS. Okay. Now, the conductance GDS, which is the partial derivative of ID with respect to VDS, is given by mu n Cox W by L times VGS minus VT minus VDS. Okay. So, let us examine these two in a little more detail, but the point is that GDS is not 0. Okay. We evaluated the constraints required for a good amplifier that provides a high gain, and we saw that y22 or GDS should be 0, but in this case it is not 0. So, that is the reason why triode region is not the desired region for operating an amplifier. Okay. You can do it, you can always set the operating point in triode region and try to make it work like an amplifier, but it will not be as good an amplifier in triode region as it would be in saturation region. So, to do that we will compare these quantities between the two regions. Saturation region and triode or linear region. Okay. So, GM value in saturation region is given by mu n Cox W by L VGS minus VT, and in triode region it is given by mu on Cox W by L times VDS. And we know that the triode region is defined by VDS being smaller than VGS minus VT. So, it is very obvious that any GM that you get in triode region is going to be smaller than in saturation region. Okay. So, GM in triode will be less than the GM in saturation region. Okay. And the GDS value in saturation region is 0 according to our model. Later we will see that it is a small non-zero value. And in triode region, it is mu on Cox W by L VGS minus VT minus VDS. Okay. The value of VDS itself will be between okay. So, this GDS will be some positive quantity. So, GDS in triode region is more than in saturation region, GM in triode region is less than in saturation region. So, any amplifier that you make with the transistor biased in triode region will have a smaller gain than if it were operating in saturation region. Okay. And you can also see that in this case, as VDS goes from 0 to VGS minus VT, GDS changes from mu on Cox W by L times VGS minus VT to 0. Okay. And GM changes from, you can see this VDS will be 0 initially, 0 to mu on Cox W by L VGS minus VT. So, these two change in complementary ways. GDS is maximum when VDS is 0, that is the transistor has no voltage across it. And in fact, the value of GDS equals the value of GM in saturation region. Okay. And it reduces to 0, whereas GM increases from 0 to mu on Cox W by L VGS minus VT. Okay. Pictorially, we will assume VGS to be fixed and this value is mu on Cox W by L VGS minus VT. So, GDS starts from here and then falls linearly to 0 and then it remains 0 thereafter according to our current model, and GM starts from 0 and it increases linearly and reaches a maximum of this value at VDS equals VGS minus VT and remains constant. Okay. So, this is the saturation region and this is the triode or linear region. Okay. So, you can clearly see that to have highest transconductance and lowest output conductance, you have to operate in saturation region.